Okay, so now we'll do the sort of second part of this lecture, which is sort of the supervised approaches. So we'll probably run out of time to cover all of this, but we'll hopefully get through enough of the slides that it's then easy to start off next week with. So this has then slightly different reading material for it. So this will sort of start to get a bit more into kind of the machine learning. So that's sort of what this supervised approaches phrase means. And then the kind of last things, there'll be some decision forests, so some ideas about sort of tree models and random forests. And at the very end, this sort of UNet approach, which is kind of the ultimate method at the moment for doing sort of segmentation style problems. And so what we'll sort of cover with this is sort of the methods, the pipelines, so how you sort of combine these different steps together well, classification, regression, and then segmentation at the end. So really all of this is about sort of how we can apply these sort of machine learning tools for segmentation style problems. And so that's really the main focus of all of this. But we'll do a few classification and regression just so that you see them and have some familiarity with them. Also, the sort of the k-means and superpixel style approaches fit quite nicely into this approach. And so the kind of the basic methods overview, this is not a machine learning class. It's not a deep learning class. We aren't going to go into a huge amount of detail about this, but as we covered in the second lecture, sort of it's important to understand this framework. So, what are, methods that are available to use? Sort of what is a classification style problem? What is a regression style problem? What kind of models are typically used to deal with them? And how can you evaluate these models? And that's really the limit of the depth that we're going to go into. We're not going to talk about sort of support vector machines and how you can optimize them. It's really just, how do you train a model and how do you predict with a model? And understanding that these approaches are sort of perform significantly better than sort of hand coding all of the complicated features that you have in images. And so the first part here is sort of this idea of training. And this is where you sort of have a model, you have parameters, and you're trying to kind of learn or fit the parameters inside this model. And so it's about putting inputs in with the outputs that you want to get and having the model somehow update the parameters inside in order to better match the outputs that you're trying to get. So that you've probably heard of this before as sort of, curve fitting or linear regression, but that you basically have a number of free parameters and you're trying to adapt those parameters so that your output is as close to what it's supposed to be as possible. The sort of next stage for this is this, it doesn't scroll anymore. Okay, I guess for some reason it doesn't feel like scrolling anymore. The next stage of this is sort of predicting. And that's where once the parameters have sort of been set, once you've decided sort of all the coefficients in your model, or weights in the case of sort of neural networks, how do you apply it to new data sets to see what your results are? And so, it's important that you want to have models that kind of once you've trained them are usable on a number of different data sets and still give good results. And once you've trained it, it's usually not possible to tweak the model after the fact. So that once you've fit your model with a bunch of data, it's kind of locked. Neural networks are, of course, a major exception to this, where you're able to have models that kind of continuously learn or that you're able to slightly retrain them based on new data. But generally, in these approaches, once you've made a model, it's kind of done. This is maybe try this again and see if it works. Okay. So again, we sort of have these simple points that we had before. where we have kind of these make blobs. It's a fairly standard test data set. And that here we have sort of X and Y positions and then groups associated with them. And so we can kind of see this rather with, with the k-means, we had this as kind of a unsupervised problem of we give it a bunch of points and it tries to figure out what the blobs might be. And here we label all of them and we're trying to make a model that's capable of predicting which blob each point belongs to. And so that's sort of the major difference there between the sort of supervised and unsupervised approach, that with k-means, we didn't have any targets it was trying to go towards. We didn't say this is supposed to belong to cluster 2 or this is supposed to belong to cluster 1. We just gave it a bunch of points and it tried to separate it. Now with this, what we're trying to do is say we actually know what cluster each one of these belongs to, and so we want to come up with a method that's able to do that well. And so this is where we get to sort of nearest neighbors or case nearest neighbors. And so now we have kind of both of those topics in the same lecture. And that's the supervised method, or maybe the supervised version of k-means clustering would be what you could call it, where you basically take a point and you say, what are the n neighbors around it that I've seen before, or the k neighbors around it, and then assign that point to that group. And so we can do this sort of, in a quite simple example that, if you have the vector sort of 0, 1, 2, 3, and that's your input, and your output is sort of I am a dog. You can make a k nearest neighbors classifier that's able to take that input and output, and you can train a model. If it means anything is a completely different question, but that you have the sort of ability to train a model with sort of whatever inputs and outputs you want. And now, once you've trained it, you can predict or sort of classify things with it, where you can now put in 0, 1, 2, 3, and you get out, I am a dog. And so, some people might say it's now understood this sequence, it's made this link, but really it's just been able to regurgitate exactly what you've put in. If you now put in a value like 1.5, it spits out M. So it's not really able to interpolate or think or do anything complicated. And if you put in a value like 100, it says dog, because that's the closest point it came to. And so now we can apply that for this blob problem that we have, where we take these blobs, we make them a little bit noisier, and now we say we want to classify our points into different groups. And so we can use this sort of k-neighbors classifier. We give it a k of 1, so we say just look at the nearest neighbor, and now we fit the model with the points that we want to put in. We can now test any point we want. And so here what we do is we just take sort of all the points on the x and y axis for the image, and we can put it into the model and have it predict what group would that belong to if that point were in the image. And so we see quite nicely what's often called sort of the decision boundary, where we have kind of what it's using to decide where, if it's in group 1, 2, or 3. And so it's, hasn't completely understood sort of the problem, but it's come up with a fairly reasonable representation for how the data are organized, with a few kind of problematic points here, where it, decided this point, these 2 points should be green, and that these 2 points should be blue, and that's probably not the best prediction. That's probably more noise-based, but again, it would depend a lot on your problem. And so we can now try to stabilize the result, and so this is why it's called k-nearest neighbors, because it doesn't just have to be the nearest point. So we can say, instead of taking the nearest point, take the average of the nearest 2 or 3 or 4 or 5 neighbors. And that now we can run that prediction again. So here we fit it with 4 neighbors in this case. And now we get much smoother surfaces, because instead of looking at just what's the nearest point, it looks what are the nearest 4 points. And so now we have kind of a much more smooth classification, where we have a model that's able to take our inputs and classify them into groups reliably. So now we can go to sort of a slightly different style of problem. That was more the classification, where you got a value in, and you were trying to decide which category does it belong to. So regression is sort of a fancier name for linear curve fitting. And it basically takes all the points you give it as input and tries to kind of fit a line through it so that you get the output that you want. It's a very basic method, but it's very commonly used. It's also very easy to interpret, even for fairly large data sets, because it's just a number of coefficients that you have. And so if you put into your model, age of a person, height, and how far they live from Zurich, and you're trying to predict how expensive their car is, then you have coefficients, and you can look at each one of those coefficients, and if it's 0.5 for age and 0.001 for height, then you can say height wasn't a very significant factor. And so that's obviously a very important aspect of a lot of these models, is that the more complicated models you use, the harder it's going to be to understand exactly what's happening. And so using linear regression, while it might not be the most complicated model you can have, it's very easy to kind of interpret. And so here we can take sort of a very simple problem that most of you probably did in Kantonsschule or high school, where you have a bunch of x points, so 0, 1, 2, 3, and then a bunch of y points, 10, 20, 30, 40, and that you can fit a linear regression to this in Python, and that you get the slope. So for the x-coordinate, it's a slope of 10, and the intercept is an offset of 10. And so it's exactly what you'd expect. And of course, this is a very simple problem. You didn't need Python to do this, but that you get the right result, it works well. And so now, you can apply this to points that are really, really far away from the point you initially had. So, you can apply it to 0, 1, 2, 3, and you get the exact results you put in. So the model was able to accurately capture your data, but you can also apply it to 100, 500, negative 1,000, and you get sort of the results out. And so we can sort of do the same thing, where we take sort of these blobs again, and instead of having multiple groups, we just have sort of groups 0 and 1, and we can perform sort of a linear regression on that. So we can fit x and y so that it's able to sort of separate these groups. And so what it gives us is now the ability, so it kind of draws this plane or whatever, where you have, for each point you put in the testing image, it can now say what the score of that point is based on this linear model. And so rather than just having these initial points or being only looking at sort of neighbors, you now have kind of a smooth linear model that's able to express that difference in your image. So now trees are sort of one step sort of beyond this. And this is sort of like a list of rules. So we won't get into all of the more complicated aspects of trees, but that you could basically see a tree as sort of, rather than just sort of a linear model, but a bunch of kind of yes or no questions that you ask. And so here we can sort of take this value, we can say, 0, 1, 2, 3 is our input, and our output is now 0, 1, 0, 1. And we put this into a decision tree classifier, and what we're able to do is produce this sort of tree out of it. And you can ignore this GINI and everything else, and you can just sort of see that if you put a value in that's less than 0.5, then it's true. Or if it's less than 0.5, then the sort of output is kind of 1 or 0. And if it's greater than 0.5, then you ask sort of the next question of, is it less than 1.5? And then, is it less than 2.5? And so you basically come up with kind of a list of rules that explains how you make a classification of a given input. And so that you can now take, the same points we had before, make a tree that fits it, if it's less than minus 6.4, if y is less than minus 6.4, and if x is less than 3.38. And you're now able to make a tree where it comes up with sort of single line cutoffs for classifying everything into different groups. And so now you've sort of split up your data quite well with a number of sort of very simple yes or no rules. So by drawing little boxes. And so what the sort of extension of this is that if you go from having sort of one tree to having a number of trees, you can kind of average their results together. And so this is similar to kind of the idea you have with k nearest neighbors, where rather than just using one nearest neighbor, you use a number of nearest neighbors. And so random forest is where you use a number of trees. And so this can be 10. It's typically more, like 100 or 500, where you then get a lot of different predictions that you're able to kind of average together. And so for that same problem, we can take the data, we can fit a random forest to it. We can say we want it to fit 2 trees. Because it's random, we sort of give it the initial seed. And we can see that the sort of first tree that it built, was this. The second tree has sort of slightly different rules to it. And that we can have a classifier here that kind of combines those first and second trees together. So that the second decision tree was kind of fairly simple, breaking it this way. The first tree broke it this way, and then we get this sort of combined classifier which uses both of them together. We could then make this sort of even more intense. You could go to 4 or 5 trees, but usually that's not really necessary. So if you go here, so it's 200, and then go, 3 trees. Don't really see it very well there, but that you basically get sort of the effect of having multiple different trees together. And so particularly as your problem gets more and more complicated, you might have to go so yeah, if we start to make this sort of messier and messier rather than the sort of simple initial problem, we can then take this and build 5 trees from the results. You can see that the trees themselves also start to get more complicated. And that we're able to get sort of results that combine the best of a number of different trees. And so you're able to sort of produce more and more complicated results by using more and more trees. And what's quite nice about these methods is that you don't have to build or write any code or setup yourself, but they're all available in KNIME and Python to just use. And so it's good to kind of understand the factors that come into them, but you're not required to spend all the time sort of implementing the details on your own. So now what comes in is this sort of idea of pipelines, is that you have a lot of different steps that you want to combine together. And this is also sort of what you do with KNIME with workflows, but pipelines are sort of more specifically for just machine learning models, where you're trying to combine a number of steps together to perform a more complicated problem. And so that, we have our sample points here, and we want to do a number of different steps. And so here, maybe the first step would be to do some sort of normalization. So we use this robust scalar so that rather than having values between, -10 and 10, we get values that are between -1 and 1. And it's sort of, some outliers, but most of them fall within this range. And so this sort of shifts our values into the same range. We can then sort of continue on that, where we break our values up into different groups. So, quantile transformer, where each one is, instead of having a continuous value, you sort of group it by the values, the number of points that show up in each group. And so this is really useful for like logarithmic distributions. Then you can do sort of polynomial features where you sort of allow every point to be combined with every other point. And so you go from having sort of 3 points here to 10 points here, or 10 dimensions here, to get all the different combinations, and this allows you to kind of make more and more complicated input for the models that you're doing. And so what we actually use these pipelines for is when we're actually trying to solve a problem. And so here, we go back to that classic problem of putting images into categories, and we'll take MNIST digits, which is one of the data sets we talked about before. And so we have sort of our image data. It's 50 images that we'll take that are 8 by 8, so fairly small, low-resolution images. And that we can make a fairly simple pipeline with this, where the first state is to flatten it. So we don't want to have images as images. We want to have them as sort of vectors, because machine learning always deals with vectors. And then we apply this normalization, and we can show the input. So the input data we have here are sort of all of these images, these 50 digits we're trying to classify. We flatten them, so they're now 64-dimensional space that we have, because we have an 8 by 8 image that we just flatten out. We then normalize it so that rather than having values between 0 and 16, the values are between sort of negative 2.5 and 2.5, more or less. And that for each one of these, we can now see the distribution. So we can go down here and we can see, at the beginning we sort of had a range from 0 to 15. After flattening, that range is the same. And then after normalizing, that range is much narrower. So there's still a few outliers, but most of them are now sort of in this narrow area. We can now apply this sort of k-nearest neighbors to this data. And so with this pipeline where we flattened it and normalized it, we can now use these models that we had before on the images the same way we used them on the blobs. And so here we sort of have our image data, we flatten it, we normalize it, and then we take sort of nearest neighbor output. And so what we can see is that we get sort of 100% accuracy. And so if we put in 50 images and use the nearest one neighbor to classify them, and then apply that algorithm to the same images, we get 100% accuracy. And so if we show here, all of the different examples were classified perfectly. If we look at the precision, the recall, all the metrics, the F1, we see that all of these are perfect. And so we've built a really amazing algorithm. Does everyone remember why this isn't a really amazing algorithm? Yeah. So we tested our model on the same data that we trained it on. And so this is sort of this overfitting problem where if you train a model on something, you need another set of data to test it on. And this is always the case in machine learning and image analysis. And so if you've tweaked your parameters to work really well on one image, the only way to show that the parameters are any good is to apply them to an image that you didn't work on before. Because otherwise, you're just showing that you're able to tweak parameters in order to make it look good. And as models get more and more complicated, it's almost always possible to find parameters that make your image look good. So here we see that if we apply it to another image that we've never seen before, it predicts 7 and the real value is 9. And if we look at it, we can sort of see why it maybe guessed 7. It's not a completely ridiculous guess, but it's definitely not a 7. Maybe it's a 4, but it clearly isn't a perfect classifier. And so, it's important for us to kind of follow these sort of holdout strategies where you have some data, you have some kind of validation set, and then you have some test set. So that, some of your data you'll use for training your model, for tweaking the parameters and what you're doing. Some of it you'll use to make sure that those parameters work really well. And that at the very end, you have this sort of test holdout that you use to make sure that your training and tweaking process really did good results. And that it's very important to keep these separate, because as soon as they start to get mixed together, you can't unmix them again. and that sort of for each parameter combination, as you're tweaking your model, as you're updating your fits, you train a model and you compute your metric on the validation set. So you always have to compute metrics on data that you haven't used to train it. But then when you really want to know the performance, what you can compare other models to each other with, then you need to apply it on data in the test set, which you've never looked at before. And so the problem is in step 2, so training validation separation, most people kind of agree with. The test separation is where a lot of people then don't see why it's so important to keep the test data separate. And the problem is, as you train models and do this validation, you're sort of optimizing another set of parameters. And so you want to make sure that you haven't overfit your validation set as well. And so that's why it's important to keep them separate. Cool. So for regression, it's sort of a very similar to the classification problem, but instead of trying to predict a class, you're just trying to predict a single number. And so with this MNIST problem, we can do the same thing we did before, whereas instead of just trying to predict the class it belongs to, we predict the value that it has. And so here we have, flatten, normalize, nearest neighbor, and instead of trying to predict the class, you do nearest neighbor regressor to pick the value. And so now we have the inputs, and we see that the outputs are sort of values between 0 and 9. And now what we can do is sort of how do we assess how well it worked. So with a regressor, we don't use ROC, precision, or recall, because all we're doing is sort of predicting a value out. And what we use for these are sort of mean squared error. So how far is the value from what we were actually trying to predict, or mean absolute error, where what's the magnitude of the difference between these two values. And so that was covered sort of quite a bit in sort of the imaging lectures before, and it's the same metric we use for these kind of regression problems. And so that we can take this value, this model that we created, and show sort of the prediction results. And so because we used one neighbor, we'd expect the prediction to be perfect. It's able to memorize all the points that we put in. If this wasn't perfect, we'd probably done something wrong. And so it's always helpful to check to make sure that that still gives you very good results. But then when we apply it to the validation set, so the data it hasn't seen before, the performance drops off quite a bit. And so here we can sort of show, for each value that we predicted, sort of along the x-axis, what the model actually gave us out. So that, sometimes for 1s, it gave 2s, or 4s, or 7s. And there we can see kind of the mean squared error is 7.7, and the mean absolute error is 1.4. And that's sort of how we evaluate that. And we can try increasing the neighbor count so that we can go to having 2 neighbors instead of 1. And that, the mean squared error drops from 7 to 6, and the mean absolute error drops as well. And so maybe this graph doesn't look quite as nice, but if these are the metrics we're trying to improve, we've done a better job. We've also seen that now that we're not using k nearest neighbors equals 1, we don't get perfect results on the input anymore, because it's now averaging between 2 guesses. And so even when your point does fall in the original data set, you don't necessarily get the exact same result out. So now, sort of why this is all being covered in this class is, how do we apply this to segmentation? And so if we look at sort of a very difficult segmentation problem, like this mitochondria problem we had before, where you have kind of sort of this noisy image, and you're trying to get these mitochondria segmented out of it. And here what we have is we sort of have these images where here's the image and then here's the labels. And so what's quite nice is that someone's already made all these labels for us, and so we can try building this model and see how it works. We can now split this image into 2. So we'll say the sort of left half is training, the right half is validation. This is usually not recommended. It's usually much better to take actually different images, or ideally images from different experiments. But to keep it simple for this case, we'll just use the same image, and we still see a lot of the problems already. It's just the same image. And so that we have, this is the image we train everything on. This is the mask we're trying to predict. This is the validation image, and this is the validation mask. And so now we can do the sort of same kind of processing we did before, where we flatten the image, we do sort of a robust scaling of it to make sure that it's normalized, and then we try to fit a decision tree. And so that we're able to get a quite complicated decision tree that takes the values of the pixels and decides what the output value should be based on what the input was. And so if it's sort of less than 0.013, it's a value of 0.067. And as you sort of progress down this tree, you add or remove values based on what you see. And so what we can see in this image is that we're able to take the input data, flatten it, rescale it so that it's all in the same dimensions, and then do this sort of decision tree. And so that we can then apply this to an image, and we can actually see what it comes up with. And so we see it's never particularly confident about anything that's inside a mitochondria, but that it performs sort of a fairly simple low-level segmentation. So it's able to identify these values as being, more likely to be in the mitochondria, and these values as less likely. And so using just one tree on the raw image pixels wasn't very useful, but we could fit a model, and we could see that, it works about as well on the full data set as it did on the training data set. And so it's generalized fairly well. It's just not a very accurate model. We can now add sort of position information. So we can go through and kind of add that feature vector with the XY position inside it. And so what we get with this is that our first image is kind of this raw input data. Then we can add X and Y. So we add sort of an X channel. We add a Y channel to the image. We then flatten it and then normalize it so that all these values fall in the same category. And that what we end up with is even more complicated rules where sort of x0 is the intensity, x1 is the x coordinate, and x2 is the y coordinate. And that, we see on our prediction mask, it gives a very weird output, but it does a fairly reasonable job of predicting where the objects in the image are. And so it's, starting to give much more confident predictions and very boxy ones, which is kind of what you'd expect with a decision tree. But when we apply it to the full image, we see that it's clearly kind of overgeneralized for this particular region, and that it assumes that everything that's in this kind of region in the image that's bright is part of a mitochondria, which is clearly not the case. And so it's done fairly well on the training data set, but it's done very poorly on the rest of the data. And so it hasn't really generalized very well to other problems. So we can now try to make it more complicated. So we can add an XY step. We can use k-means to sort of cluster the data inside, and then sort of have a random forest at the end. So we can kind of add more and more steps to our pipeline, where we now have our input data, adding the XY, flattening everything, normalizing them, reorganizing them by the sort of k-means, and then coming up with a more complicated model that does this. And so we can see that actually on the training data set, this now does phenomenally. So these segmentations are almost perfect. But as soon as you extend beyond that training data set, you have lots of very weird, strange kind of artifacts that come in. And so it did a really, really good job at this, but it's now done sort of a much worse job at generalizing beyond that. We can also add sort of polynomial features. So this is where we start to combine the different values together. And so rather than being stuck to sort of boxes with decision trees, you can now sort of start cutting off more advanced shapes. And that here again, we see that it's done a very good job at coming up with this sort of the training prediction mask, but it's, again, generalized fairly poorly. And so it extrapolates that because these two are on the edge, that everything that's outside that edge also belongs to those two mitochondria, and that's not the case. And so we can start to add smarter features. And so here we add some of the filters that we talked about before. And so here we have sort of a Gaussian blur and a difference of Gaussians. So here we can see the Gaussian sort of blurs out all the features, and the difference of Gaussians kind of gives us a nice edge enhancement in the image. And so that by adding those, we can now get a model out that gives fairly good segmentations. There's still some areas it struggles with a little bit. And it generalizes much better than the ones that we had before. And so these still don't look quite as nice as these ones here, but it's done a fairly good job at sort of performing well and not being too limited by the initial cases. We can also then start to use neighborhood, where we shift the image in X and Y and add that to itself. And so each one of these images is an image that's slightly shifted. And so here we sort of have the 3x3 neighborhood. The distribution of all of these pixels is the same. And then we can fit it all into a linear regression. And so we can then run the model, and we get something that looks slightly better than our initial approach, but still not fantastic. But it does a reasonable job of generalizing. And so when you apply it to a much larger image, it sort of keeps those trends. And so the linear regression, we chose it initially here because we can get easily understood coefficients. And so the model fits this M and B so that the output of the segmentation is sort of, at each point in your output image, you multiply this M vector, or you do the dot product of this M vector and your X feature. And so in this case, it was, the neighborhood of all the images, and then add this offset. And so for the 3x3 case, what this X vector looks like is sort of the I of I minus 1, J minus 1, the I of I minus 1J, the I of I minus 1J1 plus 1, so on. And so can anyone think of why we would do linear regression for this, or what operation this looks sort of similar to? That for each pixel, we take I minus 1, J minus 1, I minus 1J, I plus 1, J minus 1, so that we take the 3x3 neighborhood and do some sort of multiplication and addition to each point there. Yeah, so it's exactly a convolution. And so when we use linear regression, what we're basically figuring out here are what are the coefficients of the convolution that we want to apply to the image. And so what we have here now is this kernel, and each one of those points we learned using linear regression. And so what we did was sort of a fairly simple curve fitting, but with this we're able to actually get the coefficients inside the kernel in order to get sort of a better image enhancement. And so we see that this didn't do a great job. And so obviously we'd probably want larger kernels and more data to train on and fit on, but that we're able to get sort of some interesting starting points with this, and that our convolution and predicted linear model are exactly the same. And so that rather than having to do a whole pipeline, if we fit a convolution, then we can just apply sort of one single operation with convolve, cell image, and mat plus B, rather than having to put it through this pipeline. We can also do the same with sort of nearest neighbors, where we see, exactly as we'd expect, that if you use nearest neighbors and you use the neighborhood, it's sort of able to identify the signature of each one of these points fairly well. And that when you extend it beyond, it sort of does a worse job. And so tweaking the number of neighbors that it uses and tweaking the features that go in would probably make it better, but it's still, massively overfitting the data so that it works perfectly on everything it's seen before, and as soon as it's something's new, it just gives very bad results. And so then this last part, which I'll cover quickly, and we can cover again at the beginning of next lecture, if there's more questions on it, is this sort of idea of UNet. And so what UNet is sort of a deep learning based segmentation model where you sort of combine convolutions together with downscaling operations and upsampling operations and skip connections in order to make sort of a model that takes an input image and predicts a segmentation map as the output. And so how it works or how they chose exactly this model or this order of operations isn't really relevant. It's just sort of important to know that this has won almost all of the big image competitions recently, or some minor change in this, and that it's a very powerful method in medical imaging and biological imaging, and that it does a fairly good job with fairly complicated problems. And so that once you have a UNet model, which is a bit of work to actually make, but there's plugins for Fiji and Nime, which let you use and train a UNet with just a few clicks inside of it. And there's Python packages which have UNets built in as well. And so it's become sort of a standard tool in segmentation. And that we have this sort of model, we can visualize the pipeline sort of like this of how data goes through it. We can see the summary of how many different parameters each layer has, and that we have 470,000 parameters. And that we can apply it the same way we applied all these other supervised models before. And so the models that we had before, we applied with, we fit them and then, trained them and then predicted with them. And we do the same thing here, that we have sort of, this initial model, when it hasn't been trained at all, it kind of gives meaningless results. And so this is sort of the random initialization the model happened to have. And with deep learning, you can then take it, use an optimizer, and slowly sort of train this model. And so with each iteration through your data set, the model gets better and better and better. And that you end up getting sort of very good predictions from your model. So this is what it's predicting. This is what it's supposed to predict. And so it gets confused by this point here, which is not a mitochondria, but it thinks it is. And this point, which it doesn't think is mitochondria enough. But it generalizes quite well. And so even though we've only trained this on one image, it's able to segment these structures fairly well. And that we can see if we continue training and overfitting it, that we end up getting sort of the mean absolute error for the training continues to kind of go up, but for the validation starts going down, which means that the model's not doing a good job of generalizing. It's sort of maxed out. And so there you kind of get more artifacts and more sort of small random noise in your image where it becomes less useful. And so for the UNet, you're really not expected to be able to reproduce this code or to be able to train a model. You should just be aware that it exists and that for a lot of applications it works really, really well. And so if you're trying to solve complicated segmentation problems, the UNet works much better than a lot of the standard image processing metrics, particularly when you're dealing with the kind of problem where you're looking at sort of small details, structures that are sort of connected in strange ways, and you have lots of labeled data. But even in this example, we only trained it with half an image. And so it's able to be trained with very little, but of course the really good performance only comes when you're able to train it with a lot of data well. And of course, if you add augmentation and some of those other steps that we mentioned in lecture 2, you can improve the performance of this even more. But the main thing is just to be aware that these models exist, and there's some advanced exercises if you're interested that start to get into more of how these things are put together and how you kind of do this analysis. So, are there any questions on that? Okay. Well, if you have questions, you can feel free to come up and ask me. The exercises are sort of based on both of these lectures. There's some easier ones, and then there's some more advanced ones. Feel free to look at all of them. For the students who are interested, there's also a number of Kaggle exercises where you can apply this to more complicated data sets and sort of practice these different techniques on data sets where they really make the most sense. And so, yeah. I think that covers everything.